Alrighty. So here we are, we're in chapter 6 still, random variables. We're doing section 6.2 on transforming and combining random variables. All right. In this lesson, in this section, you're going to learn how to describe the effects of transforming a random variable by adding or subtracting a constant and multiplying or dividing by a constant. You're going to find the mean and standard deviation of the sum or difference of independent random variables, and we'll find probabilities involving the sum or difference of independent normal random variables. This is what we will be working on today. So first, we're going to talk about linear transformations. In section 6.1, we learned that the mean and standard deviation give us important information about a random variable. In this section, we'll learn how the mean and standard deviation are affected by transformations on random variables. In chapter 2, we studied the effects of linear transformations on the shape, center, and spread of distributions of data. Recall the following. Right, adding or subtracting a constant, A, to each observation adds A to measures of center and location, right, such as mean, median, percentiles, quartiles, things of that nature. Does not change the shape or measure of spread. So if we add or subtract a constant, shape won't change. It'll shift. It's not going to change. It's going to be the same shape. Also the spread, right? So like standard deviation, variance, interquartile range, right? Those aren't going to change either. Multiplying or dividing each observation by a constant B multiplies, divides measures of center and location by B. Right? Multiplies and divides or divides measures of spread by B, or absolute value of B. Right? So if B is a negative number, right, we're just going to multiply by the absolute value of B. So if the constant is -2, we'll multiply the measures of spread by 2, not -2. When we're multiplying measures of center and location, mean, median, quartiles, percentiles, things like that, we'll just multiply by whatever B is. So if it was -2, multiply by -2. But for measures of spread, standard deviation, variance, things like that, IQR, you multiply by the absolute value of B. And again, multiplying or dividing an observation has no effect on the shape. All right. So again, this kind of refers back to chapter 2. We're talking about distributions of data. This is what happens with linear transformations. Okay. So you need a moment to write any of this down for their notes. Please raise your hand. Right. All right, so let's look at an example using a random variable. We're going to first consider multiplying a random variable by a constant. All right, so we have our example of Pete's Jeep Tours. They offer a popular half-day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. We define X as the number of passengers on a randomly selected day. So in our table here, we have X can have the possible values of 2, 3, 4, 5, and 6. And the probability of each of these number of passengers is 0.15, 0.25, 0.35, 0.20, and 0.05. And we have our histogram over here. All right. The mean of X is 3.75 and the standard deviation is 1.090. This is some given information for our problem. Pete charges $150 per passenger. The random variable C describes the amount Pete collects on a randomly selected day. All right, so if I have 2 passengers, I collect $300, 3, 450, 4, 600, 5, 750, 6, 900. So we're just multiplying the number of passengers by $150 per passenger. And the probability for each amount of money collected is kind of just carried over from the probability of having a certain number of passengers. Right? Those probabilities aren't changing. And as we would expect, the shape of the histogram for the money collected doesn't change. Now, the horizontal axis, the x-axis, changes values. Right? Instead of number of passengers going from 0 to 6 here, we have money collected going from 0 to 900. So that has to change, but the shape stays the same. And our probability y-axis looks the same as well. Right, the mean of C is 562.50 and the standard deviation is 163.50. All right. How do you think they could have easily calculated the mean of C? What do you think they did based on what we've seen so far? How do we get from 375 to 562.50? Everybody sleeping. All right. Well, we just multiplied the mean of X by 150. Right? And we multiplied the standard deviation by 150. All right, so multiplying a random variable by a constant, the effect on a random variable of multiplying or dividing by a constant, multiplying or dividing each value of a random variable by a number B multiplies or divides the measures of center and location, mean, median, quartiles, percentiles by B, and multiplies or divides measures of spread, range, IQR, standard deviation by absolute value of B. It does not change the shape. As with data, if we multiply a random variable by a negative constant B, our common measures of spread are multiplied by the absolute value of B. Again, when multiplying or dividing by a constant, this changes measures of center and location and measures of spread. Has no effect on the shape. Right? The overall shape of our distribution will stay the same. If it was approximately normal before, it stays approximately normal. If it was skewed to the right, it's still skewed to the right. If skewed to the left, still skewed to the left. The shape will not change. So now, Adding a constant to a random variable. We're going to consider the same scenario again. Pete's Jeep Tours. We define C as the amount of money Pete collects on a randomly selected day. Right. This is the same probability distribution as the previous page. And we have the mean of 562.50 and the standard deviation of 163.50. Right. It costs Pete $100 per trip to buy permits, gas, and a ferry pass. The random variable V describes the profit Pete makes on a randomly selected day. Right, so again, we get to the profit by subtracting 100 from the money collected. And again, our probabilities of each of these outcomes stays the same. It kind of just carries over from the other tables. Once again, the shape stays the same. Our distribution has the same overall shape, fairly symmetric, unimodal, right? The range changes, right? The value of the mean changes. All those things are changing. However, if we look here, the mean changes to 462.50, right? We subtract $100 from the mean of C, but the standard deviation remains the same, all right? Our standard deviation has not changed. And just like adding or subtracting a constant from quantitative data, from the mean or standard deviation of quantitative data, this adding or subtracting a constant has no effect on the standard deviation for a random variable. It's going to stay the same, right? Think of it as we're just shifting the entire distribution up or down the x-axis. The width of that distribution, right, the range, right, the spread doesn't change. It's just shifting up or down. So then the effect on a random variable of adding or subtracting a constant, adding the same number, a, which could be negative, to each value of a random variable, adds a to measures of center and location, mean, median, quartiles, percentiles, does not change measures of spread, range, IQR, and standard deviation. Does not change the shape of the distribution. All right, so adding or subtracting only changes measures of center and location. So then we get everything together is a linear transformation. Effect on a linear transformation on the mean and standard deviation. If y equals a plus b times x is a linear transformation of the random variable x, then the probability distribution of y has the same shape as the probability distribution of x. The mean of y equals a plus b times the mean of x. And the standard deviation of y equals the absolute value of b times the standard deviation of x. Right? Since b could be a negative number, we have to have that absolute value in there. So in general, if we have a linear transformation, this is the effect it will have on the mean and standard deviation. Right. Linear transformations have similar effects on other measures of center or location, median, quartiles, percentiles, and spread, range, and IQR. Whether we're dealing with data or random variables, the effects of a linear transformation are the same. Just like the effects of a linear transformation we saw on one of the first slides. Note, these results apply to both discrete and continuous random variables. So it doesn't matter if we're dealing with a discrete random variable or a continuous random variable. This is the effect of a linear transformation on the mean and standard deviation. All right. So combining random variables. Many interesting statistical problems require us to examine two or more random variables. Let's investigate the result of adding and subtracting random variables. Right, so let x equal the number of passengers on a randomly selected trip with Pete's Jeep Tours, and y equals the number of passengers on a randomly selected trip with Aaron's Adventures. We'll define the random variable t to be equal to x plus y. What are the mean and variance of t? right? So reviewing the data we already have, this is the data for passengers and probability for Pete's Jeep Tours. And then we have the data for Aaron's adventures. Right, notice that Aaron can only hold from 2 to 5 passengers. Right, so the probabilities are, not everything matches up, and that's okay. They're not the same size, so to say, random variables, but that's okay. They don't need to be. Right, and we have the mean and standard deviation of each of these random variables, x and y. All right, so first, how many total passengers can Pete and Aaron expect on a randomly selected day? Right, saying that word expect means they're looking for the mean for the sum of those two random variables. Since Pete expects 3.75 passengers and Aaron expects 3.10 passengers, they will average a total of 3.75 plus 3.1 equaling 6.85 passengers per trip. All right. So essentially, if I want the average or expected amount for the sum of two random variables, I just add their means. I don't have to do any special calculation, just add them up. All right, we can generalize this result as follows. For any two random variables, x and y, if t equals x plus y, then the expected value of t is expected value of t equals mu of t equals mu of x plus mu of y. All right, the expected value of t is the mean of t, which is equal to the mean of x plus the mean of y. In general, the mean of the sum of several random variables is the sum of their means. Okay. And next, we'll consider how much variability is there in the total number of passengers who go on Pete's and Aaron's tours on a randomly selected day. Right, to determine this, we need to find the probability distribution of t. Right, so we'll look at that next. Right, the only way to determine the probability for any value of t is if x and y are independent random variables. All right, so before I can go about and determine probability, calculate variance, standard deviation, and things like that, I need to determine, are these independent random variables? All right, and recall, if knowing whether any event involving x alone has occurred tells us nothing about the occurrence of any event involving y alone, vice versa, then x and y are independent random variables. So knowing one can't influence the result of the other one. All right. Probability models often assume independence when the random variables describe outcomes that appear unrelated to each other.
What's that?
All right. You should always ask whether the assumption of independence seems reasonable.
Oh, yeah, definitely. They're dependent. They're on our last tax return.
Right, and in our investigation, it is reasonable to assume X and Y are independent since the siblings operate their tours in different parts of the country. It's part of the problem context that was not provided previously. All right, so since these tour companies are not in the same area, they're not taking business from each other, it's reasonable to assume that they're independent. So we can calculate probabilities. So this mess is the probability combinations, essentially. So if t equals x plus y, consider all possible combinations of values x and y. Right, so this table shows we could have 2 passengers from Pete and 2 passengers from Aaron, getting us a total of 4 passengers, and a probability of 0.045, 2 and 3, 2 and 4. It's all the combinations. All right. And multiplying the probabilities of each of those gives us the probability of that occurring. So we have all these probabilities, right, ranging from 4 to 11, and this is our distribution. Right, notice like there's multiple ways to have 5 passengers. right? Multiple ways for 6, 7, 8, and so on. All right. We already found that the expected value of t is 6.85 when we just added the means of x and y. To calculate the variance of t, we have to add up all the differences between the observations and the mean of t squared, right, times the probability of each of those things occurring, which gets us some crazy calculations such as this, right? And we get 2.0775 as the variance. So again, that's the variance. We have one more step to do. All right. But also, we had the variance of x was 1.1875 and the variance of y was 0.89. If I add those up, I get 2.0775. So essentially, we can avoid doing this calculation because these variances for x and y add up to the variance of t. All right, so I can't directly get to the standard deviation by adding standard deviations, but if I have the variance, which I can easily get from the standard deviation, right, I can square the standard deviation to get back to the variance. I can add the variances to get the variance of t, in this case, the sum of the random variables, and take the square root and I have a standard deviation. All right. As this illustrates, when we add two independent random variables, their variances add. Standard deviations do not add. We have to do that additional square rooting. For any two independent random variables, x and y, if t equals x plus y, then the variance of t is, right, equal variance of t equals the variance of x plus the variance of y. Pretty straightforward. In general, the variance of the sum of several independent random variables is the sum of their variances. So again, this helps. Right? It gives me a way of not doing all those extra calculations. Right? If I know that they're independent, I can add the variances, and then if I need the standard deviation, I just take the square root. Remember that you can add variances only if the two random variables are independent, and that you can never add standard deviations. That is not a thing. You can't add the standard deviations. You must add the variances. We can perform a similar investigation to determine what happens when we define a random variable as the difference of two random variables. In summary, we find the following. So again, I can add random variables, which means I can also subtract random variables. All right, that's a thing. So the mean of the difference of random variables is kind of what we would expect it to be. For any two random variables x and y, if d equals x minus y, then the expected value of d is the difference of the means, right? Expected value of d is the mean of d is the mean of x minus the mean of y, right? Same order in which they were listed here. And in general, the mean of the difference of several random variables is the difference of their means. The order of subtraction is important. As in all math, order of subtraction is important. 5 minus 2 is not the same as 2 minus 5. X minus y is not going to be the same as y minus x. The order in which it was provided, x minus y, is the order in which we need to subtract the means, x and y. The variance of the difference of random variables is a little different. For any two random variables, x and y, if d equals x minus y, then the variance of d is the sum of the variances. We do not subtract variances, right? The variances still add, right? In general, the variance of the difference of two independent random variables is the sum of their variances. So this is a bit counterintuitive, right? You have to remember that variances, whether you're adding or subtracting random variables, add, right? They'll always add. So we will do an example. If a random variable is normally distributed, we can use its mean and standard deviation to compute probabilities. Right? Any sum or difference of independent, normal, or random variables is also normally distributed. All right. So if we're combining two random variables that are normal, then their sum or difference will also still be normal. So we can use all the stuff we know about normal distributions with those. All right, Mr. Starnes likes between 8.5 and 9 grams of sugar in his hot tea. Suppose the amount of sugar in a randomly selected packet follows a normal distribution with mean 2.17 grams and a standard deviation of 0.08 grams. If Mr. Starnes selects 4 packets at random, what is the probability his tea will taste right? So we're going to have x be the random variable, and it equals the amount of sugar in a randomly selected packet. And then t will be the random variable that represents the total amount of sugar in Mr. Starnes' tea. Right? And it's comprised of 4 randomly selected packets of sugar. We want to find the probability that t is greater than or equal to 8.5 and less than or equal to 9. So first we find the mean of t by adding up the mean of each of the random variables, which is all the same. 2.17, 4 times, we get 8.68. We then find the variance. We add up the variances, all right? Which we do this, again, we weren't provided the variance, but we were provided the standard deviation, 0.08. So we square 0.08 4 times to get 4 variances, add them up, we get 0.0256. So we now have the mean and standard deviation of the random variable t, which is also normally distributed. Right. And again, there's our standard deviation, 0.16. We take square root of 0.0256. So then we have the information we need to now standardize 8.5 and 9 based on the mean and standard deviation of t. And we use that in the normal distribution in table A to calculate the probability. Right, so z of the lower bound is negative 1.13. The z-score of the upper bound of 9 is 2. So the probability that z is greater than or equal to negative 1.13 and less than or equal to 2 is equal to 0.9772, which is found on table A, where we have a z-score of 2, minus 0.1292, which again is found on table A, where the z-score is negative 1.13. And that gives us 0.8480. There's about an 85% chance that Mr. Starnes' tea will taste right. Okay. Again, this follows the same type of strategies that we've used with normal distributions in previous chapters. All right, and so that's section 6.2, right? We have describing the effects of transforming a random variable by adding or subtracting a constant and multiplying or dividing by a constant. We can find the mean or standard deviation of the sum or difference of independent random variables, and we can find probabilities involving the sum or difference of independent normal random variables. Right? That is section 6.2. Right. Let's end that. So there we have it. Does anyone have any questions? Anything I can clarify for you about section 6.2? Again, we will practice using these ideas tomorrow in class. Right. Well then, that is today's lesson. If you have questions, please let me know. Otherwise, you guys are free to go. That's the entirety of the lesson. If you have the time, I do recommend looking at the practice problems in Canvas. Other than that, I will see you guys tomorrow morning. Same bat time, same bat channel. Have a lovely day.